All right. Okay. So last class we discussed about the DC analysis of two important biasing configurations, which was the first one among the two configurations was the self bias, and the second one was voltage divider biasing configuration. Okay. And prior to that we had also discussed about fixed bias configuration. Okay. So just a very quick recap on the biasing configurations so that we can start with the DC analysis of the depletion type MOSFETs and also the enhancement type MOSFETs. Okay. All right. So that was about self bias configuration. Okay. The only difference between the circuit part is that when you compare a self bias with that of a fixed bias, you will observe that a self bias we use only one power supply or one biasing voltage which is at the VDD side, whereas for a fixed bias there was a need to use two separate supplies. Okay, one at the gate side and the second one was at the drain end, which was VDD. Okay, so there were two supplies, which was actually a drawback in the case of a fixed bias configuration, and that drawback has been eliminated in the case of a self bias configuration. Okay, so that's the expression for VGS. Based on the expression, you can clearly observe that the current ID is linearly proportional to VGS, right? So once the DC analysis is performed by applying KVL to the input loop as well as output loop, that's the network solution which we get. Okay, so you can clearly observe that there is a linear dependence, right? Okay. All right. Moving forward, the voltage divider biasing, which is a much better biasing configuration in terms of stability when compared to the fixed bias as well as self bias configurations. Okay, and the reason for the stability is a combination of these two resistors R1 and R2, okay, due to which a voltage divider formula can be applied so that a voltage Vg can be found out here. Okay, once this is found out, then you can directly find out the expression for VGS, okay, and find out the positioning of the quiescent point with respect to the device as well as the network characteristics. Okay, so that was the DC analysis which we had seen, and finally for plotting or for sketching, okay, you will observe that that's the device characteristics and the network solution. Okay, the network line is here. So you will be plotting the network line based on these 2 points and then just extend it so that it meets the Q point at a particular position, right? So what about the expression which controls the positioning of the Q point? So that's the expression which determines the positioning of the Q point, Vg minus ID Rs. Okay, all right. So we discussed about three important biasing configurations, the DC analysis of those three biasing configurations with respect to the JFETs. Now coming to the depletion type MOSFETs, okay, we can greatly simplify the DC analysis of depletion type MOSFETs if we are comfortable, if we have thoroughly understood the DC analysis of JFETs itself. Okay, and why is that? The simple reason is we had seen in one of our previous classes that the Shockley's expression holds good for JFETs and it also holds good for depletion type MOSFETs. Okay, except that the Shockley's expression cannot be applied in the enhancement range. Okay, so apart from that everything holds good. Okay, so when the Shockley's expression holds good for a depletion type MOSFET, then it is quite obvious that the DC analysis steps must also hold good for depletion type MOSFETs as similar to that of DC analysis of JFETs. Okay, so let us just look at those things. The similarities in appearance between the transfer curve. Yes, there is a similarity between appearance of the transfer curves of JFETs and depletion type MOSFETs because of the same Shockley's expression. Okay. So this actually permits a similar analysis of each in the DC domain. Okay. Further, however, there is a primary difference, and the primary difference between the two is the fact that depletion type MOSFETs permit operating points with positive values of VGS and the levels of ID that exceed IDSS. Okay, what do we mean by that? So if I just say that these are the characteristics of JFET. Okay, that's the characteristic of JFET. Then we'll be plotting the transfer characteristics like this. Okay, fine. And if I draw the same thing for depletion type MOSFET, then I will be getting a similar characteristics. Okay, so that's how the drain characteristics look like, and based upon which, yes, this will be for VGS equal to 0. Okay, and I will be going in a negative way. Fine. So I can plot the transfer characteristics like this, right? And that's the depletion mode. Okay. However, depletion type MOSFET also conducts when VGS is in a positive way. Okay. So when VGS is made positive, then I will be getting a higher current, right? So if I do that, but that will happen, see, this is when VGS is negative. Okay. However, I will be getting this when VGS is positive. Okay. So if I plot it, this is for this is okay. So this I will be getting it here, right? So this particular thing indicates the enhancement mode. Okay. So Shockley's expression doesn't hold good for the enhancement mode, right? So what is the Shockley's expression? The drain current ID is equal to IDSS 1 minus VGS upon VP the whole square. Okay. So this expression holds good for JFET, holds good for depletion type MOSFETs only in the depletion mode. Okay. This cannot be applied for the depletion type MOSFET in its enhancement mode. Okay. So that's the main primary difference. Okay, fine. So for all the configurations discussed, the analysis is the same. Okay, please pay attention on this statement. For all the configurations discussed so far. Okay, so which all are the configurations that we have discussed so far with respect to JFET? With respect to JFET, we have discussed fixed bias, okay, then the self bias and voltage divider bias. Okay, so these three configurations, the DC analysis holds good. It is the same for a depletion type MOSFET also. Okay, so that means if I just replace the JFET symbol with a depletion type MOSFET, then everything else remains the same. Okay. So I hope these points are clear to you, students. Okay. So I'll be giving you a small task. Okay. What you are supposed to do is that you just try to analyze the you just try to perform the DC analysis. Okay, maybe you can just note it down. Okay, so I'll be writing down the homework here. Okay, so that you can just copy it down. Perform the DC analysis of depletion type MOSFETs for fixed bias, self bias and voltage divider bias configurations. Voltage divider bias configurations. Okay, please note that there is absolutely nothing new here. Okay, we are doing the same thing. The only difference is that instead of a JFET symbol, we are replacing it by a depletion type MOSFET symbol. Okay, that's it. Okay, however, there is an interesting point to be noted here. Okay, see, with respect to a JFET, okay, with respect to a JFET, you know, for I'll be drawing the transfer characteristics like this. Okay, for a fixed bias, you know, the network solution line was like this. Okay, then for self bias it was like this. Okay, so, and for, let me select a third colored pen, and for a voltage divider, you know, bias, it was something like this. Okay, if this is ID versus VGS. Okay, now when you plot the same things for depletion type MOSFETs, okay, then you will notice that the transfer characteristic, okay, whether it will be like this or like this, okay, for a depletion type MOSFET. Okay, in any of the cases you just observe. Okay, what about the network line? Do you get it here or do you get it here? Okay, so that's, I'll just write it. Okay, check out and find the solution. Okay, I have given you the hint, so you will have to do it on your own and then, you know, just compare it with your textbook. Okay, you know, anyhow, I'll be showing you the summarized you know, network solution for all the possible combinations, all the possible configurations. Okay, fine. Then very quickly moving towards enhancement type MOSFETs. In the enhancement type MOSFETs, you will be studying two types of configurations. Okay, one is using a feedback mechanism, and the second one is the same voltage divider circuit. Okay, so these two are there in your syllabus, voltage divider bias configuration. Okay, why we have selected the first one, wherein we have a feedback. Okay, feedback in the sense, here you can clearly observe that there is a gate resistor which is being given as a feedback, okay, from the gate again to the drain, right? Okay, so that's the feedback which is usually present. Why are we interested in this particular circuit? The reason is, you know, when you start studying about op-amps, which are called operational amplifiers, there, you know, most of the circuits are based on feedback. Okay, and in the feedback, the core you know, device which is being used, they are either JFETs or MOSFETs. If they are MOSFETs, if they are of enhancement type MOSFETs, then this is the particular feedback arrangement that is being used generally. Okay, so for that purpose we are interested in this particular feedback biasing arrangement. Okay, so again, going by the steps. DC analysis. Now you know we are very comfortable with the steps, right? Okay, because the first step is itself to assume that the capacitors behave as if they are open circuits, because the capacitive reactance will be equal to infinite. Okay, so you will have to ignore the input as well as output portion. Okay, so just ignore these parts, so that the simplified circuit that remains is the one which is given in the right hand side of this particular slide. And now one more important point is the effect of this resistance, the gate resistor has disappeared. Okay, and it is obviously understood that the reason is due to, again, gate current is always 0. Since the gate current is 0, Ig is always 0, and since Ig is 0, the voltage drop will be 0. Okay, since the voltage drop is 0, then obviously it has to behave like a short circuit. Okay, so that is why the RG has been removed in the DC equivalent. Okay, so just observe. Now applying KVL should be very easy, right? Okay, at least to the input loop. Okay, what will happen if you apply the KVL? When you apply the KVL, the expressions that you get are VDS is equal to VGS. Okay, it is obviously true, right? Because now gate and the drain terminals, both of them are shorted. So VDS should be equal to VGS, right? Okay, then further, this is for input side. Okay, and when you apply the KVL at the output side, you will be getting this particular expression, VDS equal to VDD minus ID into RD. Okay, now since VGS is equal to VDS, so you can relate this expression like this also. Okay, because VDS is equal to VGS. Okay, then the two extreme conditions, because you need 2 points, right? Okay, 2 points, so that you can just draw the network line. So the first point is obtained when you substitute VGS is equal to 0. So when VGS equal to 0, please concentrate on this particular expression. When VGS is equal to 0, then ID equal to VDD upon RD. So when VGS is 0, right? Okay, so we are here somewhere. When VGS is 0, ID equal to VDD upon RD. So that's the first point. The second point is when ID equal to 0 milliamperes, VGS equal to VDD. So that's the second point. So once you obtain 2 points, just draw the line so that it intersects or coincides with or at a point on the device characteristics. Okay, so that's our Q point. Okay, please understand, once the Q point is identified, then if you just draw the vertical lines to the horizontal as well as vertical axis, you will be getting the quiescent drain current and the quiescent gate to source voltages. Okay, fine. Then moving forward to the second type, voltage divider biasing arrangement. These expressions are similar to that of the DC, which we actually discussed it for the case of JFET DC analysis, right? So that's the simplified voltage divider biasing circuit. You will have to find out VG, okay, by applying the voltage divider law. So VG can be found out by this particular expression, R2 upon R1 plus R2 multiplied by VDD. Okay, then applying Kirchhoff's voltage law, you can solve it. VGS, VG minus VGS minus VRS. VRS is the voltage drop across the source resistor. Okay, so if you apply KVL, that's the expression which you get, and once you simplify it and then rearrange it, okay, you will be getting this particular expression for VGS. Then applying KVL for the output loop. Okay, whenever I say output loop, we are applying it like this. Okay, so this is KVL for output loop, right? So this is VDD must be equal to voltage drop across the drain resistor, voltage drop across drain to source terminals of the enhancement type MOSFET, and the voltage drop across the source resistance. Okay, so there are 3 drops here, right? So that's the first drop, second drop across the device, and third drop across the source resistance. Okay, so these 3 drops must be equal to VDD. Okay, so finally you can just simplify and then rearrange it so that okay, you just obtain the expression for VDS also. Okay, so these things are straightforward and very simple. Okay, you may be asked some problems based on these particular expressions, but note that if there are any problems being asked, then they will be pure substitution based problems. Okay, very simple problems. Only thing is that you should know how to analyze that particular configuration. Okay, first of all you will have to identify that particular circuit. Okay, does it belong, see first of all whether the device is a JFET depletion type MOSFET or an enhancement type MOSFET. Okay, that should be your first identification. Then once you identify the particular device, then you will have to identify the particular configuration, right? Whether the circuit belongs to fixed bias, self bias, or voltage divider bias. Okay, that should be your second step. And once you identify that thing also, then the third and the final step should be the DC analysis. Okay, fine. All right, so let's try to quickly summarize, right? So we started off with JFET fixed bias configuration. So that's how the fixed bias configuration looks like, and these are the pertinent input as well as output expressions, and that's the graphical solution. Then self bias, VGG supply has been eliminated here, and the pertinent expressions, the graphical solution. Then finally the voltage divider bias, the circuit or the configuration, the pertinent expressions, and finally the graphical solution. Okay, see, it is called graphical solution, because based upon the graph the Q point has been obtained. Okay, the same thing can also be obtained mathematically. Whenever we say mathematically, we will be using Shockley's expression. Okay, fine. Then again the depletion type MOSFETs. Okay, just now I had mentioned that the DC analysis for all these 3 configurations with respect to a JFET holds good for depletion type MOSFET device also. Okay, because Shockley's expression holds good. So just compare, right? The configuration is the same. The only difference here is that we have a depletion type MOSFET, right? Okay, there is a small error here. It should have been a depletion type device. Okay, by mistake they have just placed a JFET. It should have been this particular device. Okay, fine. So in the pertinent equations, just observe that the only difference here is instead of minus VGG, it is plus VGG. Okay, so what does that result? When it is plus VGG, when VGSQ equal to plus VGG, then the network line will be on the right hand side of this particular graph, not on the left hand side as it was in the case of JFET. Okay, right? Okay, so this is what I was asking you. Okay, then for depletion type voltage divider, just observe. Okay, it's the same thing. And enhancement type MOSFET, okay, just now we looked at it. And finally enhancement type voltage divider configuration, that's the thing. Okay, fine. All right, so I think we are done with the DC analysis of various configurations using different type of transistors, especially JFETs, depletion type MOSFETs and enhancement type MOSFETs. Okay, fine. So, in the next class we will be starting off with our third chapter, which concentrates on small signal analysis. We can also call it as AC analysis. Okay, so far what we have done relates to the DC analysis. Okay, just to add one more point here. See, in all this DC analysis, 2 points were very important, right? Okay, and those 2 points were that we nowhere, just be writing it here. Okay, note. Okay, nowhere we considered varying voltages. Varying voltages were not considered here. Okay, in the sense we sticked on to only fixed voltages were considered. Fixed voltages were considered. Okay, and whenever we say fixed voltage, we mean to talk about DC voltages. And only because fixed voltages were considered, the Q point that we got, okay, you can consider any of the configurations, the Q point is fixed here. Okay, there is just a single Q point, right? However, when we, if at all we considered varying voltages, see, it's not mandatory that this VDD should be a fixed voltage itself or a DC. Okay, it could be DC or it could be AC also, right? Okay, VDD may vary. So, in that case, what should we do? Okay, what if VDD varies, or what if we are performing the AC analysis so that input as well as output signal are now to be considered? Okay, see, when input and the output, okay, both of them are included, then we will have to consider the coupling capacitors also. Okay, so all those things come under small signal analysis. Okay, so we will be discussing on small signal analysis what actually a small signal means. Okay, I'll just put a question to you so that you can reply me in the next class. Okay. What is a small signal? Okay, and you may also find that if you just Google it out, you will also come along an expression called large signal, small signal versus large signal. Okay, so just try to understand the difference between these two things, so that we will be discussing upon these aspects in our next class. Okay, so whether small signal, does it really mean that a sinusoidal signal is so small? Okay, and large signal, does it really mean that a big amplitude based signal? Okay, is it this thing or is it something else, right? Okay, so we will discuss on it in our next class. Okay, all right. So if there are any